Good morning everybody. Today I will discuss the one of the most significant welding process, specifically in the category of the solid state welding process, that is friction stir welding process. So, this process is now widely used and extensively used for different applications. So, specifically this welding process actually development started by the application of the relatively soft material like aluminum or aluminum alloy, but nowadays this welding process can also be used in welding of very high melting point material and very hard material. So, let us look into that, the basic understanding of this friction stir welding process. So, actually it is invented in UK in the year 1991, and after that there is a lot of development still going on, and specifically it is having so many advantages as compared to the fusion welding process in terms of that specifically for dissimilar combination of the material, and at the same time that fusion welding also creates a lot of hazards and then some environmental issue also in case of fusion welding process. So, in that respect friction stir welding process is very clean process. So, it is also called the green technology, and because of this energy efficiency and environment friendliness, because in this case there is the machine itself consumes the electrical energy, and then there is no formation of the any gas and any kind of hazardous materials during processing of this during the welding process, during this solid state welding process. So, in that sense it is called, it is also called the green technology. So, basic principle of the friction stir welding process is that there is some we can use some electrode. What sense we use the electrode in case of the fusion welding process? Here we can use that non-consumable rotating tool, and that rotating tool creates the frictional heat generation between the two contact surface. Of course, it is also necessary to provide some relative motion between this tool and the workpiece surface. So, that generates the heat, and that heat actually better plasticize the material around a very defined zone or very small zone, and then after plastic stirring the materials can be joined, and for in any combination in the sense similar kind of material as well as dissimilar kind of materials can also be joined by this process, but at the same time the maximum temperature within the system will never cross the melting point temperature. So, it is a one kind of the solid state welding process. Now, if we look into in details about this process schematically, if you see that two material and the different joint configuration, and nowadays bar as well as the lap joint both configuration, the welding can also be done using the friction stir welding process. So, in this case the two materials lap or in the bar configuration we can keep, and at the interface of this material we insert the tool and then start moving the tool. So, two kind of movement of the tool, one is the rotational movement of the tool that actually helps to frictional heat, at the same time transport. So, that is called also the welding speed, to move gradually the tool from one specific direction, that also helps to make the joint between the two surfaces. So, there is a in this case the main part of this friction stir welding process is the design of the tool, so that it will be able to steering the plasticized material and make the mixing between these two, between the material, and finally make the joint. So, this friction stir welding process mostly at the start at the very beginning it was started like that, converting the simple milling machine process to in terms of the friction stir welding process. So, in the milling process we use some rotating tool, and that we can hold the we can try to rotate the tool, and that tool is inserted in the workpiece, and then transverse movement of this rotating tool helps to make the solid state joining of these two materials. So, if you look into the different terminology or maybe specific term related to friction stir welding process, we can see that tool, there is a friction stir welding tool, but there is a at the end of the tool there is a tool pin. That pin is actually in contact with the two workpiece, and that normally this tool pin is more or less the height of this tool pin is equivalent to the thickness of the material. So, this there are some specific geometric dimension that depends on the thickness of the materials, or maybe some limitation of the power, rotational speed, all actually makes the factors to define the size of the geometric tool. It can be cylindrical, it can be tapered also, but there may be some for the more flexible or more mixing of the material by plasticization. It can also provide with the some kind of a thread on the tool pin also. So, there we will see the different types of tools normally used in the friction stir welding process. But here if you see there is a weld central line, that is the interface between the two workpiece or two substrate material, and there is a welding direction, which direction the tool rotating tool actually moves. But normally the rotational speed is very high as compared to the welding speed of this in this process. There is a two things, that tool shoulder we can call, if you look into the figure itself, that tool shoulder is actually contact on the surface of the material, but tool pin is actually inserted to the depth of the material. So, tool pin actually covers the whole depth of the material, at the same time shoulder surface actually covers the only on the top surface of the materials which is supposed to join. So, here the leading edge, that in the advancing side we can define the different terminology in the way looking into the relative velocity or the direction of the rotational velocity and direction of the welding speed or welding direction. Based on that we can divide whether it is in the advancing side or whether it is retreating side. But in the front, which direction the rotating tool moves, front side is normally called leading edge of the rotating tool, and the behind side is called trailing edge of the rotating tool. Now, the main objective of the friction stir welding is to generate heat at the workpiece surface, and other objective is to move the material such that you will be able to join between the two materials. Therefore, frictional and deformational effects results in actually plasticization of the material. So, with this objective we can define the advancing side and retreating side. The advancing side is defined that with the sense that similar tool rotational speed and the transverse direction of the tool is the same side, that is called the advancing side, and retreating side that it is just opposite, that means which direction tool is rotating, that means linear velocity of a point, that is tool rotational speed and the transverse speed of the tool are in opposite direction. So, with respect to the weld central line we can define one is the advancing side, another is the retreating side, depending upon the direction of the rotational speed as well as the transverse speed of the tool. Now, in friction stir welding process there are different stage. That means, if you look into the complete process, first is that there is a after fixing the workpiece surface or substrate material, then it is necessary to brings the tool is in contact with the workpiece. So, that initial period when the just at a fixed position or maybe at a fixed axis, the tool is given to the vertical motion towards the workpiece surface, such that is called the plunging period. maybe if you look into this figure, first phase is the plunging phase and we divide the total time phase of the friction stir welding process. So, in the plunging phase, the simply without any translation movement of the tool, just gradually inserting the tool pin inside the workpiece, and after plunging up certain time, it takes some time for this plunging operation, plunging phase. Next is the dual phase. So, in the, or we can say that it is the initial dual phase. So, once the plunging depth is completed, then we keep the tool at the fixed position for a certain time, that is called dual time. So, once the dual time over, then we start the actual welding process. So, that means welding starts in the sense that the rotating tool just starts moving to the transverse direction or along the welding direction. Then gradually during the welding directions, once it reaches almost at the end of the workpiece surface, then we can assume that the welding phase or welding period completed. After that, gradually we keep it the final dual, that means at the end position at the fixed location, that means on the workpiece is kept for certain time. Of course, within this certain time, the tool also keeps rotating, and once this final dual phase is over, then gradually the plunging out means we gradually remove the tool from this at the end of the workpiece, and that plunging out, of course, there is a vertical movement of the tools occurs, but without any welding speed of the tool. So, these are the typical phase of the typical time phase of the friction stir welding process. But apart from this thing time phase, we can divide the friction stir welding process also in the different metallurgical processing zone. So, this will be more clarified if we look into the actual microstructure of or macrograph of the friction stir welded sample. We can easily identify at the different zone, but let us what we can divide all this kind of the material processing zone. First, normally friction stir welding is in other sense is more closely related to the metal forming process, that means hot metal working process, and it resembles the mechanisms of extrusions and the forging during the process. So, therefore, friction stir welding process can also be modeled as a metal working process in consecutive, I think, conventional 5 phases. We can divide this different metallurgical processing zone or maybe different phases here. First one zone is that is called the preheat zone, then initial deformation zone, extrusion zone, forging, and finally, the post weld post heat or cool down zone or maybe cool down period. So, this 5 metallurgical zone we will see how it looks like. So, from the figure, if you see that in this figure, if you can define that rotational direction of the rotational speed, I means whether it is a clockwise or anti-clockwise direction, and the direction of the welding. Based on that, we can say that in the front size, that is called the preheating zone, and then is the initial deformation zone, and then just around the tool, that is extrusion zone actually exists in the around the tool. So, that extrusion mechanism prevails during the welding process around the tool, and then behind this back side, that is the forging zone, and finally, remaining part is the cool down zone. Because in this, when you try to define different zone, we need to clearly define that the direction of the tool rotation as well as the direction of the welding. So, from the figure, it is very obvious that welding direction also given by this arrow. I think in one direction it is moving, that means the welding direction is towards the preheating zone. That means that in the ahead of the friction stir welding, in which direction the tool is supposed to move in the preheating zone and initial deformation zone exist. And then near about the tool, the extrusion zone, and behind the tool, that is forging zone and then cool down zone. And here we can see that looking into that direction of the tool material, rotational speed of the direction of the tool material, that means clockwise or anti-clockwise direction, and at the same time welding direction. Here we can define that the advancing side and the retreating side. So based this mechanism actually exists to different zone. We can explain in that way that preheat zone ahead of the tool pin is in this case basically temperature rises due to the frictional heating of the rotating tool, and at the same time there is a cause of temperature rise for the other reason, that is called adiabatic heating because of the deformation of the material. So, in this case friction stir welding process there is a high deformation of the material. So, that means this mechanical energy is converted to the thermal energy without any loss. So, therefore, that is called adiabatic heating process also occurs due to the deformation of the material. So, both are responsible, frictional and mechanical deformation, both frictional heating and mechanical deformation both are responsible to raise the temperature in the preheat zone or in overall all the within the friction stir welding process. Therefore, the thermal properties definitely and of the material and the transfer speed, that is a very sensitive parameters of the tool, actually governs the extent, that means size of the preheated zone, and it actually decides the rate of heating of this zone. So, rate of heating mostly influenced by the transfer speed, and if we assume that thermal properties of the different types of material remain same, then transfer speed actually play the role to decide the extent and the rate of heating of the specifically preheating zone. After preheating zone, that the tool moves forward and initial deformation zone actually forms, and in the initial deformation zone the material is actually heated above a certain critical temperature. So, deformation happens in such a way that the temperature rise reaches above the critical temperature, and of course, at the same time the maximum amount of the stress exceeds the flow stress value. So, once this condition reach, then material starts to move there, that means most of the cases the materials behave like the viscoplastic material. So, material flow starts at this zone. So, this material in this zone is actually forced both upward into the shoulder as well as the downward into the extrusion zones. It will be very clear if you try to look into this a schematic picture here also. If you define the different zones, we can see that the extrusion zone is near about. So, that extrusion zone is actually exists just surrounding the FSW tool, and remember the friction stir that means tool is moving along this direction. So, that is the welding speed is this direction. So, therefore, ahead of this tool there is a material flow. So, with respect to that point, some materials are forced to flow upward and some materials are try to flow the downward direction. Of course, this material flow is also restricted by the on the top surface there is a tool shoulder. So, tool shoulders actually constrains the material flow also. So, that this zone is basically initial deformation zone, and that initial deformation zone actually starts creating the conditions for the start of the material flow. And in the extrusion zone, if you see in the extrusion zone also the finite width, that means very small narrow zone, we can find out material also flows around the tool. So, even within the extrusion zone the material also flow around the tool. Then critical isotherm on each side of the tool, and actually this when you try to do some modeling approach, then we can define mathematically the critical isotherm each size of the tool defines the width of the extrusion zone. So, extrusion zone can also be mathematically defined by looking into the isotherm, and the magnitude of the stress temperature are insufficient to allow the metal flow. In the certain part, wherever we can define that certain part, whenever define the metal flow that with respect to the temperature isotherm and the condition for the material flow here, or sorry, condition for the magnitude of the stress, by looking into that we can decide whether there is a metal flow or not. So, therefore, material flow is actually very limited to around the FSW tool, and the extent is very less. Then the next part is the if you look into that, beyond that, if you go beyond that zone, that is the forging zone. So, in following the extrusion zone is the forging zone, where the material form in the front of the tool is forced into the cavity left by the forward moving of the pin. In the extrusion zone, with a finite width, we can find a very small zone, that is the extrusion zone, and in this extrusion zone is confined, and even material may also occur in that extrusion zone, and that is a very narrow width of the corresponds with reference to the friction stir welded tool. So, that magnitude is very less, but if you go beyond that, there is a forging zone, but of course, in the if you away from the extrusion zone, that actually the size of this zone is decided by the critical isotherm, and basically the flow stress condition or maybe magnitude of the stress and temperature, that actually define whether there is a metal flow occurs or not. So, that means from the above, from the extrusion zone, next zone is the forging zone. So, in this forging zone, the material is in front of the tool is forced into the cavity left by the forward moving pin, and that also condition exists, the hydrostatic pressure condition on this zone. So, apart from this extrusion zone, so behind apart from this extrusion zone and this forging zone, behind that there is a post heat zone or maybe cool zone, where the materials actually cools down under either passive or forced cooling condition. So, the solder, but within this, if you already discussed the material flow, and even for the initial deformation zone or maybe around the extrusion zone, that material flow having some constriction, that means restriction of this material flow is imposed by the presence of the solder, and that put the some constraint and may change the flow direction depending upon the size of the solder that is actually in contact with the workpiece material. But material flow within the solder also, because solder also create the sufficient condition, that means the temperature and the flow stress value, that the flow material flow also occurs depending upon the pattern of the direction of the solder. So, material from the solder zone is dragged across the joint from the retreating side towards, it comes from the retreating side and towards the advancing side. So, pattern actually depends on the rotational speed, that material flow condition, and at the same time also depends on the forward movement of the tool, that means welding speed. So, depending upon all these parameters, they create is a very complex material flow pattern during the friction stir welding process. Now, if we look into that, the friction stir welding process having the different kind of joint configuration. So, from the figure it is very much obvious that both butt and lap joint configuration can be possible using the friction stir welding process. So, if you look into that figure A actually it is a butt joint configuration, that means two materials are in contact, and the interface there is a movement of the tool, and that creates the certain amount of the nugget zone, and that nugget zone is nugget zone, and finally, it creates the joint between these two plates. So, this is one type of the configuration of the joint that can be done using the friction stir welding process. If you look into the B, that it looks like the L pattern, the two materials are kept in such a way, and then, but basically it is a butt joint configuration. The two materials can also be done in this configuration also. If we look into the C, in the figure C, that we there are two weld zone has been created here. So, although overall structure looks like the T, but if it is necessary two different materials or maybe two similar kind of materials or maybe three different types of the materials, but these two weld joint can also be produced using the friction stir welding process if we use the two different rotating tools. Two different rotating tools can also be possible using this type of weld joint configuration. If we look into that figure D, that also lap joint configuration. So, that means two metallic materials can also be joined using the lap joint configuration. So, here the weld joint is maximum covered on the top materials or the top components, but less covered in the bottom components. But of course, anyway these two materials can be joined in this way, that is the that means in the lap joint configuration, and of course, multiple components can also more than two components in the lap joint configuration can also be done. That is very much obvious in from figure E also. Here I think three materials, three different thickness or similar kind of thickness can also be joined. So, one advantage of this type of lap joint configuration is that the material thickness not necessary to be the same. The thickness of the material can be different also. At the same time, the two different types of material can also be possible joining using friction stir welding process. But if you look into butt joint configuration, but with two different thickness, it is not very straightforward like the joining of the similar kind of thickness material. So, little bit there may be some difficulty arising when we try to join two different thickness of material at butt joint configuration, but that may not be the case in case of lap joint configuration. Similarly, if you look into the figure also, this is the one kind of T joint. So, that T joint is that one single two different materials are joined here, but that fusion zone covers it is a I can say it is a one kind of lap joint configuration, not the butt joint configuration. So, in this case the fusion zone dimension covers on the top surface on the top component completely, and then little bit to the bottom component, and it creates the joint in that this lap joint configuration. And if you look into G also, here also friction stir welding process can also be possible, but here if you see that is the kind of L joint, and it is joining the two materials, but here you can say it is not straightforward like the lap joint, or even it is not straightforward like the butt joint configuration. So, with that these are the typical type of joint configuration we can make using the friction stir welding process. That means that till the process is developed in such a way that this kind of the this kind of the configuration can be possible using the friction stir welding process. Now, in friction stir welding process actually involves like other welding process so many process parameters, but the main process parameters involved in the friction stir welding process, that is tool rotational speed. That tool can be moved in the clockwise or anti-clockwise direction, and this tool rotation actually results the steering and mixing of the material around the mainly around the tool pin. Therefore, if tool rotational speed is very high, normally heat generation will be more, because when the at the high rotational speed the frictional heat generation will be more, and that creates the intense mixing and steering of the material. And second parameter, that is the tool transfer speed. Normally this speed, this that also we can say it is the welding speed. So, this speed is also very less as compared to the tool rotational speed. So, in this, the providing the tool rotational speed or welding speed, that actually creates the joining of the two materials, between the two materials, and that depending on that the length of the weld joint can be decided. Other not important always or maybe important parameters, but normally we do not see, that is called the tool rotation rate. Sometimes we use the friction welding process, the tilt tool. So, say tilt tool can also be used. That means, if you want to try to use the friction stir welding at the different configuration of the weld. So, it is also necessary sometimes to tilt the tool. So, that we can provide certain angle also, and that kind of, that can be, that we can say it is a kind of secondary parameter is influence the basic friction stir welding process. Other parameters apart from that tool rotational speed and tool transfer speed, other process parameters, that is the plunge depth. That means up to what depth the tool pin can be given, so that the sound weld joint can be obtained. It is a kind of if you want to compare with respect to the fusion welding process, that when you try to join two different two materials, maybe similar or dissimilar materials, the intense objective is to cover the full depth of penetration. So, either using laser or any other kind of arc, different types of the arcs. So, full depth of penetration normally we achieve very in case of laser welding process. So, that full depth penetration, similarly if we want to do the full depth welding in case of friction stir welding process, then it is necessary to design or define the length and the strength of the tool pin. Strength in the sense, that means dimension of the tool pin, the diameter and the length ratio of the tool pin, that is attached with the actual friction stir welding push through the shoulder. So, therefore, tool pin, size of the tool pin, or we can say the plunge depth, we using the actual friction stir welding process, that actually decide whether it will produce the shallow weld profile or whether it is provide the deep plunge depth profile. It will produce depending upon the amount of the plunge depth we can provide during the friction stir welding process. So, if we see that for the definitely for the producing the sound and the smooth weld surface, normally we prefer the deep plunge width, because if we provide the shallow plunge width or shallow, if that is very small plunge depth, if we decide, that means this, if small plunge depth means the depth is very small as compared to the thickness of the material, then most of the cases we cannot move the material from the front to back, and pin actually produce the with the surface of the groove with kind of tunnel or maybe kind of inner channel. So, it is not advisable to use the shallow plunge depth during the FSW if you try to get the successful weld joint. So, rather deep plunge depth is more suitable in case of joining of the two materials by FSW. So, here if you see that the workpiece produce excessive flash, produce significantly concave weld, and finally leading to the local thinning of the plate. That means that steering or material flow is very confined, is within a small zone, that is around the tool pin, but that is why if you want to achieve full depth of that means full weld joint, that means up to the full depth of the workpiece. Therefore, tool pin size is almost similar to this, the thickness or depth of the workpiece material. Apart from that, there are several other welding process parameters. For example, travel speed, this in general, the travel speed, that means welding speed, the spindle speed, rotational speed of the friction stir welded tool, workpiece thickness, flange depth and flange force, definitely joint offset if there is a necessary for joint offset, joint gap between the two metal when they are in contact, if there is any mismatch, joint mismatch, and that means different thickness of the material, and tool geometry. All actually parameters or an optimum combination of all these parameters is able to produce some successful weld joint. So, therefore, travel speed normally if we look into the individual parameter and its general effect of all these parameters, it is like that. Travel speed, it is normally very low, that means we need to put that welding speed gradually the movement speed of the welding will be very low. It is like a, we can compare that in machining process, what we can give the feed motion and what we can give the cutting motion. So, it is resembles the feed motion during the machining process. So, that is why travel speed or welding speed should be followed very low. Then spindle speed. So, spindle speed should be very high, because that there is some I think in each and every process in a material combination, material and tool combination, there may be some minimum tool rotational speed to get a good weld joint. So, normally spindle speed is very high. So, that will be able to produce the frictional heat generation, and that heat generation basically soften the material and finally plasticizing, that helps to plasticizing of the material. Third parameter is the workpiece thickness. So, if workpiece thickness is very high, it may be like that, it is very difficult to plasticization of the material exactly at the bottom of the workpiece plate. So, there is some optimum thickness of the material for a specific tool geometry, but normally we can find out that 4 to 6 millimeter thickness of the material of aluminum alloy or aluminum alloy can be able to successfully join using the conventionally existing tool or whatever tool geometry. It is possible to join between these two, but if the thickness is too high, then it is very difficult. That means, thickness is very high means it is necessary to provide, if you want to provide the steering action of this material even at the bottom of the workpiece material, then it is necessary to extend the length accordingly, the length or height of the pin is also required. So, if pin height is very high, then there is the chances of the breakage of the pin from the actual friction stir welding tool. So, we cannot make the very sufficiently large tool pin. So, there may be some optimum values. So, that means it's necessary to optimize the geometry as well as that length of the pin. So, pin length having certain limitation. So, therefore, if there is a limitation on the pin length, accordingly there may be some limitation of the workpiece thickness. Up to that point, we can do the welding process, we can do the welding of the two materials by FSW successfully. Second is the flange depth. Depth means using the pin up to what extent we can give the depth of the tool. That means, it is basically flange depth is more or less equal to the size of the height of the tool pin. Flange force, that means during the plunging force there is some, it is necessary to put that to solder in contact with the workpiece surface, to hold the workpiece surface and to make the constant material movement also. There is some axial load is required from the tool. So, that load is also important parameter such that during the process whatever force will be exerted on that, and that will maintain the steady state welding of the workpiece material. So, that force is can be measured also, and that force is very one of the significant parameter in friction welding process. Then joint offset. Joint offset means the offset can be done just to movement of the tool just towards either one sided of the material. That means, it is not always that means it is not always true that this joint offset is specifically important when you try to join the dissimilar combination of the material. So, there is a dissimilar combination of the material having the huge difference in the thermophysical properties. So, therefore, heat generation and the resistance to the mechanical load or flow stress value all are different in these two cases. So, to control the mainly to control the intermetallic compounds during the fixed state welding of the dissimilar materials, then tool is normally offsetted to one sided. So, normally if we try to join between copper aluminum, so one is the harder material, another is the relatively softer material. So, tool pin is normally shifted towards the softer material, so that the volume mixing between the aluminum copper can also be controlled by simply offsetting the tool. So, this way it is also one another significant parameter for joining of the dissimilar materials. Then joint gap as the important parameter, up to what extent we can keep the gap between the joint or it is a tight control between the joint is also necessary. That depends the type, nature, joint configuration also and practical limitation also. So, based on that joint parameter or joint gap can be a one significant parameter for FSW process. Then joint mismatch, sometimes the two different type of the thickness of material can also be required to join. So, that if thickness of the material are different, then parameter selection of may be different as compared to the similar thickness of the material. So, that is also another important parameter. And finally, the tool geometry. Tool geometry in the sense that tool geometry sometimes the two component of the tool geometry actually which is in contact during the FSW process. One is the tool shoulder, that is in direct contact with the surface of the workpiece material. Another is the tool pin, that pin is actually in contact between the two surfaces which is supposed to join. So, there are several ways to modify or to incorporate the different design of the tool as well as the surface of the shoulder. Shoulder surface can be very flat or can be concave or convex depending upon some advantage or on that, and at the same time pin is mainly the responsible for the mixing of the between the two materials. So, therefore, pin surface can be very straight cylindrical tool or can provide it is a kind of conical shape or can be different shape, different geometric shape along with the some threaded profile on the tool pin, that actually helps to mixing or plasticizing of the material. So, there is a geometry of the tool is another important parameters, and that actually influence very much on the successful weld joint. But if we look into the overall advantage of this fixed state welding process, we can summarize overall advantage of fixed state welding process like that. First is the metallurgical advantages. So, metallurgical advantage is first is that it is a solid state welding process. So, it avoid any kind of the complexity in solidification that may arise in the fusion welding process. So, all the phase transformation happens in the solid state. So, in that sense it is advantageous because solid state phase transformation happens in the mixing, forming some of the intermetallics all in below the melting point temperature of either of the material. Then normally we can find out the fine microstructure. So, this is another advantage. So, almost equiaxed fine microstructure we can find out in the nugget zone, and that is because of the condition temperature and strain rate or deformation condition in friction state welding is relatively higher side. So, that actually produce the creates the mechanism of the recrystallization. So, normally in case of aluminum or aluminum alloy we can find out the continuous dynamic recrystallization. So, that due to this mechanism the grain refinement mechanism. So, very fine grain can be produced within the structure. So, fine microstructure, that is the one added advantage in the FSW process as compared to the other welding processes. Excellent properties in the joint area. If the joint can be produced without any internal cracks, without any defects, then the weld joint properties is very high and almost similar to the base materials can be produced using this friction stir welding process. Definitely low distortion of the workpiece, which is a severe problem in fusion welding process. So, here distortion is very minimum. Then dimensional stability and repeatability is also very high in friction stir welding process as compared to the other welding process. Specifically, it is very advantageous as compared to the fusion welding processes. No loss of alloying elements, like in laser welding, there is a formation of the keyhole and there is a maybe some alloying loss of the alloying elements happens in fusion welding process. So, in that sense it is advantageous because no loss of alloying elements, because temperature is limited up to the below the melting point temperature, and absence of cracking, specifically the cracking in the sense the solidification cracking we did not find in this friction stir welding process, because the principle itself is the temperature is below the melting point temperature. Therefore, the cracking normally do not find, which is more prone to happens in the fusion welding process, and that is not in FSW process. So, that is another big advantage of this FSW process. So, if we look into other environmental advantage. So, in the very beginning we pointed out that friction stir welding process is one kind of green technology. So, in that sense it is having very advantageous, because no shielding gas is required, no surface cleaning is required, no grinding waste, no solvent for degreasing, no consumable materials like filler material, flux, rod, gas, etc. are required. So, these are the typical requirement of all the shielding gas, surface cleaning and all these things, that means consumable, that actually is related to the fusion welding process. So, in that sense it is more environment friendly process, and that is why it is called the one kind of the green technology. Now, if we look into that, we have discussed that this is the friction stir welding process. Now, we look into that friction stir welding tool normally used for these things. From the figure, if you see that different types of tools can be used during the processing, we can just have a look the different types of the look. If you see, the first one is the straight cylindrical tool pin, and straight cylindrical tool pin, just pin which pin is extended from the tool shoulder surface. So, tool shoulder is here, is the tool shoulder surface is flat, and then apart from that part the pin is basically formed, and that pin is in the size of the pin is very small as compared to the shoulder diameter. So, diameter of this very less in this case, that also follows in friction stir welding process, and it is the geometry is like that. It is called a straight cylindrical tool pin with a flat cylindrical shoulder surface. If you look into figure B also, here you can see the straight cylindrical parts square threaded tool pin. So, it is also pin geometry is the cylindrical, but with square threaded tool pin. And if you see the figure C also, straight cylindrical, but V threaded pin tool. So, all if you put in the different kinds of the threads on the tool pin, that actually directly influence the material flow pattern during the FSW process. Fourth one is that tapered cylindrical tool pin. So, straight tapered cylindrical tool pin without any thread, and if you other tool profile is that tapered cylindrical square threaded tool pin and tapered cylindrical V threaded pin tool. These are the normally, apart from that we can create the different geometry of the tool pin, but all these cases different types of the tool pins is definitely having some influence on the material flow pattern, and finally, it actually influences the weld joint properties as well, because this profile, that means thread profile, changes the flow pattern of the material during the steering action of the two different type of material, and that finally influence the weld joint properties. And of course, not only the flow pattern, also at the same time the frictional head generation are different, because although it is a pin height is same, but the spin surface which in actually contact with the workpiece material, the surface area are different in all these cases. So, therefore, since surface area difference, so heat generation during the frictional action will be different for all these cases. That means, it finally affects the temperature distribution as well as the material flow behavior within the material. So, although this type of tool profile we can use it, but when you choosing the tool material, that means what should be the material of the tool, they should have some kind of basic properties or should follow. First is that the tool material should have high compressive yield strength at elevated temperature, because most of the because this tool is basically subjected to highly compressive stress. So, therefore, compressive yield stress is very high even at very high temperature. Then that is the one desirable properties of the tool material. Next is the dimensional stability and creep resistance. So, dimensional stability, that means even it is at very high temperature condition, it can retain its hardness, and at the same time creep resistance properties should be very high. That is the another desirable properties of the tool material, fixed tool material. And thermal fatigue strength should be very high, because this tool material is always is in repeated heating and cooling cycles, it is subjected to that. So, that repeated heating and cooling cycles can create some kind of thermal fatigue. So, good thermal fatigue resistance, good fracture resistance, and of course, low coefficients of the thermal expansion, all are these desirable properties of a tool material. So, based on that, the typical tool materials are used in the high speed steel, nickel alloy, metallic carbide, ceramics. These are the common materials we used, and all these tool materials actually we can recall that what we use for the metal cutting process, what are the typical types of the tool we just use in metal cutting process. So, almost similar category of the tools material has been developed that are actually used in the fixed stir welding process. But high pitch tool still we use it, but at the same time we can use, for example, that depends of the tool materials is not is actually difference between the mechanical properties of the workpiece material and the tool material. For example, if that in general the tool material should have some hardness difference with respect to the workpiece material, which is supposed to join by the FSW process. For example, in case of aluminum, simple aluminum, pure aluminum, that can be joined just by simply using stainless steel SS304 or SS316 can be used as a tool material for joining of the simple aluminum, pure aluminum. So, therefore, like that, even when you try to join some harder material, so tool material should be more hardness as compared to the substrate material. That is the general principle of choosing the any material. So, apart from that, the material should have this kind of desirable properties just we have mentioned. So, all these desirable properties if exist, then we can use the tool material. But there is a separate analysis of the tool material, because here also other side of the tool material or tool which is used for FSW is that tool wear and cost of the tool to produce the any kind of weld joint. That is also different aspects of the analysis, that is in this case that is the beyond the scope to analyzing the effect of the tool and the cost of the tool in FSW process. Now, we just simply try to look into that other aspects in the fixed stir welding process, because we have mentioned that milling machine is normally used as a fixed stir welding process, since that there is a rotating tool, and the rotating tool is we put into the flange depth, certain depth, and we just simply hold the tool under rotating condition. Therefore, certain amount of the axial force, at the same time some torque is required to maintain the welding process during the welding. So, we look the typical variation of the axial force. If we measure it, and using some dynamometer we measure it, that force. So, if you look into that different phases of the friction stir welding process and the typical profile of the axial force that was acting during the FSW process. So, here if we use the tool material as SS304, workpiece material AA1100 is almost pure aluminum, thickness of the workpiece material was 6 millimeter, and corresponding welding condition, rotational speed was 1100 rpm and transfer speed or welding speed was 98 millimeter per minute, and in this case we have used the straight cylindrical square threaded pin tool. So, solder surface was very straight, geometry of the tool pin was the cylindrical, but along with the square threaded. And here if you see the plunging phase, if you see the plunging phase means gradually inserting the tool inside the workpiece material without any transverse movement of the tool. So, in this case when you try to just insert the tool, there is a gradual increment of the force, because more and more the tool is more and more the rotating tool pin is interacting with the workpiece surface. So, throughout the whole plunging phase, the complete insertion of the tool inside the workpiece, and that increase gradual increment of the force. Next is the dual phase. In dual phase, if we see that once it reaches the maximum value of the force during the plunging at the end of the plunging phase, and when they start the dual phases means we just keeping the we just simply rotating the workpiece at this desired position. So, we want to try to establish the keep on increasing the dual phase means there is a more heat is generated and softening the material. So, therefore, mechanical force, axial force required is less. So, that means in during the dual phase there is a gradual decrement of the force, axial force, and once after that, once we just start moving the rotating tool in the welding direction or along with the welding speed, then at the start of the phase, then again gradually increases the amount. That means, magnitude of the force requirement will be high, increases linearly, and then once the welding phase done, there is a continuous movement of these things. It creates some almost steady state condition, that means constant force movement, and once that is obvious from the figure also. So, once the welding phase is over, then with the plunge out of the tool during the plunging of the tool, that means disengagement of the tool from the workpiece. So, gradually the force will be reduced to the 0 at the end of the welding process. So, this is the typical picture of the axial force at the different welding phase. Now, we can do related to the fixed welding process, we can do some simple mathematical calculation, that is the how to estimate the heat generation assuming the simple cylindrical tool with the straight cylindrical pin profile and of course, flat solder surface. So, before doing this calculation, we assume from the figure that is the tool solder, the tool bottom of the tool solder is in contact with the workpiece material, and also tool pin is also in contact with the workpiece material, and solder radius is R s with respect to the axis and pin radius is R p. Now, if we assume the theory that heat generation is due to the sliding and the sticking friction condition, actually we can divide the heat generation due to friction in general into two components. One is the sliding friction, another is the sticking friction condition. So, sliding friction is generally follow the Coulomb's law of friction, and based on that we can find out, if we assume that frictional law, and then we can estimate the amount of the heat generation. And sticking friction means at the certain part the metal is in stick with the workpiece material, but not necessary if the all contact surface are in the either sticking or sliding condition. Maybe up to certain part is in the, I think very initial part is in the sliding mode, and the remaining part in the with the sticking with the workpiece material. So, based on this sliding and the sticking friction condition, we can divide the elemental heat generation dQs into these two components. So, one is the this friction condition ds dqf, and this is the sliding condition and this is the sticking condition. So, these two components of the total heat generation is to divide into two components, but it is very much difficult to find out the up to what extent there is a sticking and up to what extent there is a sliding condition prevails during the friction rolling process. So, in that sense here we can define, one is the contact state variable, that is the V matrix by V tool, that is the ratio of the velocity between the matrix material side and the velocity of the tool is the tool side. That means, if delta equal to 1, that means V matrix equal to delta equal to 1 is equal to V matrix equal to V tool. It indicates that metal is moving along with the same velocity of the tool. So, that condition prevails. If delta equal to 0, that means V matrix equal to 0, that means there is no material flow at all. So, that is the two extreme condition. So, that we can divide in these things up to certain part, it is a sticking and maybe not 100% sticking, or maybe certain percentage in sticking and certain percentage in sliding condition prevails here. Then that it is better explained with the with the state variable delta. We assume that first is the del dqf. So, that means I think sliding component, that means frictional heat generation due to the sliding components, it is 1 minus delta, that means some part is the for due to the sliding condition, and then velocity equal to omega into r, and then tau contact, that means contact shear stress value, that means at the contact surface what is the shear stress value, and then dA is the area. So, that shear stress into elemental area, that actually represents the basically shear force. So, that force into velocity, actually force into velocity, that actually defines the amount of the frictional energy, and further this energy we divide into these two components, one is the 1 minus delta, another is the only delta. So, only delta, that means it is a sticking condition, we can say only delta omega r tau contact into dA. But point is that what way we can divide, what we can decide the contact shear stress value in these cases. If we know the contact shear stress value, then it will be possible to find out the actual heat generation. But if you look into the expression for that dq, the simple velocity into elemental force in this shear force, so omega r into df, and for the cylindrical component, then omega df can also be represented by the elemental area. So, d theta into dr. So, if it is a circular component, it is, if suppose this is d theta and this is dr. So, that actually represents the this area. So, then r d theta into dr actually represents that elemental area. So, from here we can find out that r square d theta dr omega into tau contact, and if you look into that, defines the range of the this diameter or radius of the shoulder, then we can find out this thing. So, here we can actually we are trying to find out what is the heat generation when the metal is in contact on this surface, actually on the shoulder surface. So, then Q can be integrating over 0 to 2 pi, that means theta varies from 0 to 2 pi, and radial distance from this radial to this. So, that is the r from r p with respect to r p to r s, that is the range of that, and if we do, we can find out that q equal to that 2/3 of pi omega the contact shear stress value and the r s cube minus r p cube. So, this estimates the amount of the heat generation on the shoulder surface which is in contact with the workpiece and the shoulder surface, but excluding the part of the pin component. Now, it is necessary to define the uniform contact shear stress value at the contact surface. So, there is a we have defined in the two different conditions that the contact surface is the one is the sliding and the sticking conditions of the friction. So, then it is better represented that the contact due to the sliding friction condition, tau friction equal to mu into P, coefficient of the friction, and P is the pressure on that. Pressure means that pressure can be calculated from the axial force, and that axial force is here is if you know the axial force and divided by the cross sectional area whichever it is distributed, and that cross sectional force divided by this cross sectional area, that actually define the pressure. So, that this defines the sliding friction condition. So, tau contact should be replaced by this from these sliding conditions, and if and which part the sticking conditions prevails, in that case, that since we are assumed the sticking condition. So, here it is reasonable to assume the shear stress value is equal to the yield shear stress value. So, yield shear stress value better represented by the sticking condition. So, if we put the corresponding value of these two at the two different conditions and sliding and sticking component, then we can find out the Qs, which defines the amount of the heat generation at the on the tool shoulder surface in case of friction welding process. And if we see that here it accounts the shear yield stress value of the material, and of course, it accounts the extent of the sliding and sticking by incorporating the contact state variable delta, and it should know the pressure that comes from the axial force, and then what was the diameter of the tool pin and diameter of the shoulder. All actually the simplified way we can find out the amount of the heat generation. So, the similar calculation can also be done if tool pin bottom surface profile is in contact is with the workpiece. So, what is that? Tool pin bottom surface creates the generates the amount of the frictional energy or heat generation, we can find out also in the similar way, but here the range of the surface it should be from 0 to Rp, that will be the range of the radius in this calculation.